Yeah, now just let us revise what we have seen last time, and then we can continue further. Last week on Monday, just we started to see some design requirements. What are the requirements that we need for controlling robot motion? Yeah, and also for modeling, the geometrical modeling, and for the mathematical modeling. So that one is we are going to deal in next chapter. So from the geometrical perspective, there are geometrical or from physical requirements. There are some requirements specified by standards. These standards can be from DIN EN ISO 10218. There are two versions, first and second. I said there are old versions, and actually the 2018, this 2018 version was revised. Yeah, we are actually like it in 2020, so we are going to use that one. Yeah, just I started to record it actually. I will load into Moodle or something else. Just if it works, yeah. So I started to record it now. Then maybe we will see. But the question is, I don't know actually how it could really handle it. But just I will tell you at the end of the sessions. Already I'm now recording. Okay. So we have two standards. These standards are from 10.21.8, and the other is from the TS 15.066. The 15.066 is mainly designed for collaborative robots where the human and the robots work together in a shared environment. But outside that, if the human is not collaborating or not sharing the robot working space, then how does the safety requirements could be ensured? So that's the main requirement. So for this reason, there is a safety standard which mainly deals with the hazards and some features and parameters that you have to take into account whenever you design your robot. Or, for example, if you want to come up with a new robot brand, for example, then you need those features to include in your product. So this can be considered from the control perspective, from the mechanical design perspective, from the positioning. Are you really sure that the robot will stop whenever you say stop at 10 at the joint variable of, for example, theta 150 degree, theta 230 degree, something? So it doesn't really stop at that specific position, joint position, or is there any kind of errors that could affect later on the motion of the robots that could be really potential for a danger or maybe for some kind of accident? So that's what we have to take into account. The other one is about the auxiliary axis. For example, if the robot is fixed at one position, or is it attached to some kind of sliding, or maybe some kind of mobile robot, and so on. So these things are also has to be defined with auxiliary axis. So that is also a safety, because if something happens, then there could be potential problem. So that's how we are going to discuss, deal, and address it. Yeah, some other things about stored energy. For example, if you have a spring in your model, then how do you handle that spring and so on? This should have to be addressed. And the other is about electromagnetic compatibility, about the electrical and the pneumatic parts of the robot. This also has to be addressed, and in the safety parameters. Actually, we are not going to deal with it today because we have to proceed to the next topic. So having said that, I would like to proceed to the geometric modeling. So from the geometric modeling, actually, we have to, last time on Wednesday, we have seen how to model the robot using, how to simulate a robot using a process simulator, for instance. So in this process simulator, there are so many features. First is the robot model. So you need a robot model. Then you need a controller, you need a path planner, you need a sequence planner, you need a task planner, you need a kinematic controller, then you need a sensor, and so on, you know. So this process simulates. So we had a chance to see different features. So, you know, we have here parts and the resources. From our resource, we have reference frame, base frames, and we have kinematic chains. Yeah, so these kinematics have their own kinematics mechanism. So this we saw it in the robot kinematics editor. Yeah, we say that there are connections between each joint. The connection between each joint was handled by the robot link. And these joints are performing a rotational motion or a prismatic motion, just depending on your interest, or depending on the design or configuration, actually. And then here we use K9 and the K8, actually. These are mainly designed for making robot gripper able to move, you know. So the robot gripper has to also move. So for the robot gripper, we have a kinematic structure, you know, for this robot gripper as well. Actually, the good thing is, you know, in the process simulator, we have color markers, you know. These color markers are actually, they are indicating which part is handled by this kinematic editor. So, you know, what we need is we need a kinematic. So we need a kinematic. So how do we get the kinematics? It's by the mathematics, right? Just by having rotational and the translational motions together. So we have to how to develop a kinematics, a robot kinematics. So that is compulsory for our case. So we are going to deal it later. But before the kinematics, what do we need is a geometric modeling. You know, these are geometry modeling. So this geometric modeling, can be in a wireframe, or it can be in the realistic, or in, for example, this is a kind of wireframe. So we could have a lot of approaches for this, but what I would like to talk about here is, so what kind of files really do we have to import into process simulator? So which model files are supported? So that's what we have to know. Once we know that, actually, then we can continue. So first, what are the file types or the file exchange formats for such modeling? In general, there are various file formats. One could say STP or STEP. The other person can say JT, other person can say STL, some person can say IGS, others can say SolidWorks or CATIA or something, you know, models. So now my focus is which is really more compatible for our study. Which one is more compatible and which one is not. And also, what is the difference between STP, STL, JT, and so on? You know, whenever you model some models, you have an option to export in different file formats. These file formats could be in GT or in STL or something. But in process simulate, actually, what we need is, one, we need information regarding the we need information regarding color, because if you see this robot, you have a color, so we need information about color. One, so we need color. The second is, what is this color? The second is we need, for example, if we select the guy from here, maybe not here, from this. we have vertices, okay? So we have vertices, you know, the models are connected from one vertex to the other vertex using a line command, okay? So there is a line which connects one vertex to the other. So we need a vertex information. So we need a vertex or these corners, and then we need a line information. So how long is the line, and then how thick it is, you know, so the thickness or the width of the line, and the length of the line, and the color of the line, yes, and the vertices are also important, okay? So what do we need? You need color, you need vertices, you need line length, and so on, such informations. Okay, so what about the kinematics, about the joint constraints? That's also what we have to gather, right? So this process simulator needs also this information. So this kind of interconnection between the links, which we call it a constraint in geometric modeling, was exported in a file format like XML or something like that. So we have XML file format, which gives information about the kinematic chains. So we need these things, okay? So these chains were actually given in the kinematic editor, okay? So just we need a XML file format which gives this information. So in general, from the requirements actually that could really provide us all this information is the COJT or JT file format, okay? So COJT or JT file format is the file format that could potentially provide you all this information. Others, yeah, others are all possible, but the question is about the memory consumption. So how much memory is consumed for one model, for 1 meter by 1 meter, 1 meter cube object? How much memory do you consume regarding the information about the vertices, about the line colors, textures, yeah, just, you know, all such features, about the frames and so on. So you have to yeah, deal with these things. So regarding this, actually, if you read those file formats, HTTP could provide information about color, yes, about vertices, about line lengths, line widths, and so on and so on. That's absolutely perfect, but it doesn't provide you about the kinematic information, you know. So maybe something you will lose this kinematic constraint. The other is JT, provides all the information, and that is a native file format which is applied by a Siemens PLM software. So in general, with the Siemens PLM software, COJT or JT is native file format. So we use JT file format. SCTL is actually the simplest file exchange format for models. It stores only the information about the vertices and the line. Yeah, it stores only about the vertices. Yeah, and IGS is actually it's more similar to STP, but with yeah, some details. And then there are others actually. Yeah, just it's up to you actually. If you are really interested, you can go through, you can get in depth and then check all the file formats. There are also other file formats like object, DAE, which are being used for a robot simulation in game environments, for example. So if you are interested, you can go to object, DAE, FBX, you know, there are so many approaches actually. Yeah, so just that depends on your interest. If you are interested, yes, you can go. Okay. Actually, for example, you know, for STL file format, it's a kind of triangulation. So it's a combination of different triangles to make a model of a rigid body or some kind of object, you know. So in this case, there are, for example, to represent a cube, there are different ways of representation of the triangles to form the cube. So, for example, for a single cube, there is about 8 vertices. No, 8. 1, 2, 3, 4, 5, 6, 8, and there are multiple lines actually. So, yeah, it depends if you can see to that, but it is the arrangement of all these vertices that makes the STL. This is actually its file format in ASCII, so it's human readable. Of course, there's also a binary format. Yeah, that depends. If you want, you can go through. So now for robot components, actually these are the exploded formats, file formats in SolidWorks. This file was exported into JT file format, and it makes this robot that you are looking here. Create this robot. So initially you could model this robot in either of the modeling tools like CATIA, if you like, or SolidWorks or NX or something like that. So finally, once you model it, you have an option to export it into JT files. Or if there is no actually supporting for functions, maybe you have to do some conversion. There could be some methods where you could do some kind of conversion, okay? So now just let me show you a simple thing. Here you could have a cube. We may extrude it. We could have some cube, like, yeah, some object like this. And then we could have a function which help us to export into HTTP, IGS, AutoCAD exchangeable file format like BSA for DWG, CATIA support server file format, and there is also about JT. Actually, this is MX. It is Siemens PLM based software. So you have also a VRML, PNG, and something. If you want to have a 2D. So here you have JT file formats. This JT file format, as you see, it says model 1.jt. So it is a kind of tessellation. It is a kind of tessellation. So you can tessellate it if you want, maybe in some customize. You can customize it, So you can tessellate it into different parts. You can define your resolution and so on. Yeah. So if you can export either a part or an assembled structure, for example, like a robot. So this robot is an assembled structure. It can be, yeah, you have an option to export it in both approaches. Yeah. So if you have assembled parts like this robot, you can have assembled parts, or you can have a part, yeah, assembled product or a part. Yeah. Yeah, so this is our approach. So you are free now just to model your robot, or there is an option actually to download these robot models from the suppliers. For example, KUKA has a service. Actually, it will provide you all the data that you need for some, for example, let's say they checked actually if we have some CAD models. Yeah, for example, which do we need? Maybe we need, yes, maybe we need a robot, KRC4, maybe KR. Maybe this is the robot I know, so maybe we have this. So we want to have a download for CAD model. So if you see it here, it is a parasolid model. It is a parasolid. Here it is STEP. Here it is some kind of UG. Actually, I don't know if it's UG, but we don't have any other files. So actually, we don't have any JT file or any other something. So if I want to use this model actually for my project, you know, what I should do is I will download maybe the STP file format or parasolid, or maybe, or I will download 3 of them, and then I will try to convert this in the process in maybe in SolidWorks or in CATIA or something, you know. So I would like to check if the other softwares work, so then you can directly check if it is supportable. Yeah, maybe in SolidWorks, I don't know, let us check if there is a possibility to convert these STP files or parasolid files, you know. Maybe we can see it here as well. We go to file, imports. What kind? Actually we have parasolid, okay? So even in a next file, you know, you have a parasolid, import parasolid, then export into IG. Yeah, then you export into JT file. So you are fine here, you know. If you have NX files, NX software, you can directly import, process it, export it, okay? So this is one possibility. In the same manner, you have to check actually if other softwares are also capable to do that. Maybe SolidWorks actually taking some time. So there is such possibility. Yeah, this is to show you. So you know, you can download the para model and then actually one thing that I want to know to tell you is in process simulate there is one file server actually where you have to locate all your libraries. The first is the project is where you name the project name, and the system root is the place where you are going, where you store your models. You know, for example, I can paste the parasolid here. Yeah, maybe we can extract it here. Yeah, okay, so we have it here. So we go to the next, for example, just we create a new. Then maybe we try by dragging it here. Maybe I don't know if maybe it doesn't work. Maybe it works. I don't know. But I think it didn't work. So we have to import it with parasolid, just to see if we have the kinematics, all the kinematics interconnections for this. Then the data. I have a system root where I store my data. My model here is the one I want. So okay. Yeah, so I got all these things. Maybe I do some kind of thing to check if all the properties are there. Yeah, so this is the robot that already I imported now. This is actually the same robot that we have in our lab. Maybe you have seen it or not. We have this robot in our lab. Maybe, I don't know, just maybe I will show you where we have it. Yeah, okay, so this is our lab. Yeah, so in our lab, we have this robot. This is our homepage, actually. On our homepage, you see this robot. So this is a KUKA KR60 jet. So this robot is sliding on the top, you know. So I downloaded the same robot here on my NX file format, and then, yeah, then it's up to you. Then after actually to take this robot for your own simulation. So there are, yeah, parts actually maybe. Yeah, so maybe this is actually personally I don't like this one. Yeah. So this is our robot. Actually, there is still something missing. Okay. This is something we missed. Okay, so now once we have this model, actually the next step is to export it, right? So we do export into JT. Okay, so now I have this file format here. Everything is, I will take the default load configuration file from this. Okay, then I will save it in output file. Where do I save it? I will save it in maybe in my system roots. In tutorial session, maybe I will say. Okay, so now we are done. We are successfully done. So the next step will be to import this into your process simulate. Yeah, actually, this is when you import it, then you are going to have some kind of robots, but this is a session that you have to do it in the tutorial section. Actually, today we focus more on the theoretical part. So then my idea, just my aim was to show you that we have an approach to model a robot, the geometrical model. And then also I was aiming to show you that we have a data exchanging file formats, which should have to be converted from one format to the other format, because all the file formats are not supported by the simulation tools. So we mainly want for this particular session a JT file format. So how do we convert this different file formats into JT file formats? So it's pretty easy. We can use, for example, NX file like, and maybe there is an option also with Katia. Maybe just let's check if we are lucky. If we are lucky, then we could have. If not, then we check for another softwares. Okay, so is there any import option? Home, what is home? Maybe here, file, then okay, so I don't have really that much experience with SolidWorks. It's a long time ago. But I think we use the open approach. Then let's check if we have the same, if we can read really. Okay, then we check here if we have the file format that we need. If then, wow, we are lucky. We have JT file, so we can export, we can import. Then we have a parasolid. Let's check it. We have a parasolid as well. So we are lucky. So SolidWorks also can be used, you know, so we can use a SolidWorks, and I will say maybe I have a Parasolid here, and I will say this one is the one I want to import. Yeah, let's check it. Let's check it if it works. Then, oh, that's nice. Even, yeah, this also really looks nice. Do I rotate? Should do, is there any? It's not rotate. It's not. Maybe let's try our button. Yeah, sorry, I don't. My experience with this is really too long. But I think it should work something like, where is the view? Oh. Yeah, actually. Yeah, then just leave it then. If it is, yeah, it's really taking a lot of time. If I don't have it, toolbars. This one here, okay.
With your wheel of your mouse, you can
because
I think you can move it.
Yeah. Yeah, the problem is I'm connected from a remote actually. My mouse has no function. Okay. I am using a Logitech mouse. It is configured on my PC, but I'm accessing from a remote PC in office. So
okay,
that's a problem.
Normally, if you press the wheel of your mouse.
Yeah, it should work with the wheel, of course, but my wheel is not working. That's a problem. Okay, anyhow, that's not our case actually right here. Our maybe I should try something like this. Okay, so just my intention is to show you that if there is an option to export as well here. So here JT file formats. Let's check JT file formats. The RML is already there. If there's any JT. Do you see any JT file formats here? So this is a disadvantage. It has no export function, so okay. Yeah, that's a disadvantage actually. So we have a reading, but we don't have any exporting options. Okay. Yeah, so we are not lucky. We could able to read, but we cannot make writing. So yeah, so that's no problem. We could export with the NX. Now let us come back to our lecture here. So here, you know, we can assign, we can model, we can define different frames, we can define our kinematics chain and so on. Yeah, and we can export out and then do it. The other thing is, you know, while you have to do the kinematics, you know, you have to also consider how to avoid some kind of collisions, then how to avoid a collision with self, with a self robot with its own link or with its own join, and how to define all your sequences and so on. That's actually we have done it last week, not last Wednesday, and also we will repeat it. We are going to do it also the next time. So that's not a big thing, but this is just to show you. You have a product, different models as a product, assembled product, or as a part product. Yeah, so these features could be downloaded and exported. Yeah. Yeah, so just having said all this, I would like to talk about the robot components. So in general, from this, you know, what we have is robot. You know, whenever we talk about a robot, what we have is one is a robot link. The other is a robot joint. This robot joints can be rotational motion, or they can be prismatic motion. So prismatic motion means a motion that translates from one point to another point, and the rotational motion means a motion about a joint axis, which changes this angular position. Okay. So in a robotics, actually, these are the two fundamental joints. Of course, there are different kind of joints that we have studied in mechanical design or something like that. Yeah, where we have seen different mechanisms of machineries. You know, maybe you have studied how to use a different kind of mechanisms to generate a motion, to multiply force, to multiply speed, or something like that. But in robotics, actually, the most common is to translate or rotate an object, or fly, or move. Whatever it is, you know, whether you fly or whether you move on the ground with navigation, or whether you are at the stationary to make some kind of cyclic operation. The overall is the basic behind is you have either a translating joint, which allows the robot links to move from one point to another, or there is rotating part, which allows the robot to change its angular position. So the change of these angular positions or the translational positions are allowing the robot to make just to be more flexible, for carrying out, for conducting any activity that it's assigned for. So still let us redefine our scope. So I would say let us focus more on revolute and rotational joints. So even, you know, for example, for one woman, you know, you could have different kind of joints, like hinges, like ellipsoid joint, maybe pivot joint, maybe ball and socket joint, or maybe saddle joint, and so on. Actually, you know, some of them are maybe really complex to model it, you know, or just to model it even in the geometrical, you know, just to find the kinematics that allows the robot joint to make, for example, a ball and socket. It's difficult, you know. Have you seen any robot which has a ball and socket joints? Maybe yes, maybe no. Maybe there are some. I've seen some on literatures actually, but how do you control exactly the infinity degree of freedom? You know, outside the ball constraint, you know, about the socket constraint, outside the socket constraint, the ball has a very infinite joint degree of freedom. So how do you really control this motion? Yeah, that's really difficult, you know. So how do you control that? You use a motor, or use cables, or some pulleys or something, you know. It's really difficult. So yeah, for example, hinges are of course possible, that they are possible. Even I wonder if you say that we could have ellipsoid joint, you know, maybe saddle joint could be, but still that's also not easy. Yeah, so that's really difficult, and maybe there are a lot of maybe in future there could be a lot of development to come, but now these are the two joint configurations right now. We do have the one I mentioned, just either for prismatic or for revolute. Yeah, so this is what we have seen last time, so it's nothing new here. Yeah, just maybe just at the last of this lecture, actually, what is maybe better to see. about the different robot configurations, actually, about the axis configuration and about the robot type. For example, you could have a Cartesian robot, a cylindrical robot, a polar robot, a parallel robot, a vertical arm robot, something, yeah, just some circular robots. Maybe you could have a horizontal arm robot, just like a SCARA robot, for example. Compliant robots. These compliant robots could be also possible. With a combination of rotational and the circular motion. Now, the robots that you do have here are performing rotational here, translational here, and rotational, yeah, rotational, then here translational. Rotational, nothing. Rotational, this is rotational, yes. I could better use. Okay, so for example, here we have a Cartesian robot. So in this Cartesian robot, there is about this axis, there is rotational, and about this axis there is translational. So this was given in this one. Okay, so there is translational here, and there is rotational here. The same is true here, rotational. Actually, here it's not. It is translational here. Sorry, translational and translational. It is translational. Sorry, yeah. Sorry for the confusion. It is translational. Or everything is. Yeah, so here, if I got it here, translational, this also translation. Yeah, just I got the call. There's I think someone is. Yeah, sorry. Sorry, yeah, I'm back. Just actually, I got a guest was calling from the outside. So, okay. So now, just what we have been saying is there is translation motion here, and there's translation motion. So whenever we have such cylindrical robots, yeah, for the example, in this situation, no, yeah, for example, for this, there is rotation of the base and there is translation up and down. Actually, the notations that we have been using here are, for example, for translation, you can use some kind of like this for front view. And for the top view, you can use some kind of like this to show that there is a translation. To show there is a translation, okay? So, yeah. For a rotation, actually, people use most of the time some kind of like this from front view, or some use some kind of yeah, some kind of like this, or also it's possible if you use something like this. Also, it shows there is rotation of joint about this axis. Actually, this parallel robots. It is, for example, we have such robots called flex picker. I don't know if you have seen it in there. It is some kind of like this. It's a delta robot. Just some people also say it's delta robot. It is it has a parallel linkage which is actuated by motors around this. So it's really very fast. You know, for example, if you compare from our robots, this KUKA, do we see the speed, for example, here? No, actually, the speed was not given here, but this is really very fast. It could operate up to 10 meters per second, up to 10 meters per second. It's very fast, you know, for very fast assembly operations. This is really an ideal robot at a very small distance. You know, you cannot make, of course, a huge, large translation and motions, just but for very specific, you know, for in a very small working space, it is really a fastest robot which can operate up to 10 meters per second. But for other robots, for example, for the KUKA or for others, the maximum speed that you can achieve is maybe 4 meters per second, maybe, or even maybe less, 2 meters per second. But with this flex picker, with the parallel robot, you can achieve 10 meters per second. And so where your production speed matters, you know, if you have fast products, for example, for either whether it is an assembly or for a pick and place operation, you know, such kind of robots are really very efficient. But if you have some slow motions like welding or maybe like painting operation, something like that, then others like manipulators are also very efficient actually. So whenever we select a robot, of course, we have to consider regarding our job. So what is the job? Is it a handling operation, or is it a painting operation, or is it a welding operation, or is it a picking the press operation, or what is the kind of operation that you are looking for? Then what's your working space? Do you have a large workspace where the robot has to make lots of tools from one position to the others? If that is the case, then you have to consider maybe Cartesian robot, or maybe a cylindrical robots or polar robots actually. But if you have a very small, again, very small configuration with faster speed, then parallel robots are maybe an option. Actually, here, you know, there's Arbeitsraum here. It's the working space. Cartesians have a rectangular working space. Cylindrical robots have a cylindrical-like working space. This is the operating space where the robot can perform a given task. You know, for a polar robot, it is kind of spherical with spherical. Actually, for this parallel robot and for this vertical compliant robots, actually you have the same thing of the same kind of operation. For kind of this parallel robots, the working space is only limited to this conical shape. For this robot, for the SCARA robot type, for example, you could have something like that. Actually, I have one question, of course. why is this is open? Why is this open? Why is this open? Why is this open? Is there anyone who could give some comment about that? Or is it like that? Or is it, yeah.
Hi, I think that's a forbidden place. Cannot we operate over there because
sorry, I hardly able to hear you. Can you repeat one?
Yeah, so Mr. Tuli, I was saying that probably that is the forbidden workspace because the robot cannot operate over there because of that safety reason you have already described in the previous slides in our lecture.
Yeah, I totally agree. And yeah, thank you very much. And yeah, that's a restricted region where the robot shouldn't, yeah, because if it has to do like that, you know, there could be some kind of collision or maybe some damage or something, you know. So we make some kind of restrictions or joint limits to avoid any potential problems. Yeah, so that's all about from the modeling perspective. I think this is this will, yeah, I hope you got some insight how the robot is going to be built, yeah, geometrically, and then how we are going to take this geometry into a simulation platform. This simulation platform, it can be a process simulate, it can be a gazebo environment, you know. I don't want to restrict you in some vendor, you know. Here what we have, we can model a robot in any file format. Of course, we have a lot of file formats, you know. You can program it in DAE, you can program it in, you can model it in DAE or in object or in STL or in DXF or in or in IGS or in STEP or any file format. Then you can convert that into supported file formats. For example, if you want to ROS, if you want to use ROS, in ROS, STL is possible, DAE is also possible, you know. So you could convert the model into DAE or STL, and then in STL file formats, you can create a URDF, a robot supported file format. Then in URDF, then you can create your robot kinematics chain, and then you can simulate actually in ROS environment. Also, you can use yeah, for visualization gazebo or movie. That there are some options. You can use it in gazebo or remove it, and then yeah, just do it. The other option is also you can use this into gaming environments like Unity 3D. I think I have shown you last time. In Unity 3D, actually, what I did was from my project. Actually, I think I have shown you last time was I exported the robot model. This, for example, my robot. This robot model has yeah, just has components. You know, it has a component. It has a component, and these components are defined in URDF file format. So URDF is not yeah, it's not something magic. In ROS, it is very common, so you know you can easily understand how the URDF is written. It is some kind of XML file format. It is called a maybe, which has something like this. You know, it has something like this. So there is a child, for example, base link. Then there is link 1, link 2, link 3, link 4. So it creates some kind of hierarchy. It creates some kind of hierarchy where you define all your yeah, joints. So this is actually, it was give, for example, if you see here, warlet is the warlet, base link is base link. For example, now base, this is base link. Use it here. For example, here, this is my base with frame, shoulder, shoulder is here, this frame. Then upper arm link, this one is upper arm link. And then I have forearm link. Forearm link is this one, this guy. This is forearm link. And then you wrist link. This is the wrist link. The reference frame was defined like this here. You know, this selected one is reference link, and wrist one, and the wrist two is here. This is wrist two, but the reference frame is here, given here. Actually, then wrist three is the last point. All these are actually, you know, they are sequentially, they are kinematic chain. A robot, this such kind of robots are a kinematic chain, so they are defined in a sequence manner. Okay, so they are defined in a sequence manner, and accordingly you can place your model. You know, you can place it in your environment. Actually, I use Unity because, as you see, it is really has a great graphical rendering, and it provides me an interface to connect the real robot to this one, you know, through the Ethernet cable using IP and port numbers. In the same manner, you know, I have a possibility to combine with the different models like human models, like the conveyors, you know, the conveyor that you see here. Flexibility to have virtual factory simulation, something like that. So yeah, so in this situation, actually, I have used STL file format and DAE file format. Actually, there are two files. One is in STL, you know, the problem is you cannot visualize the color, you know. To visualize the color, actually what I used was, you know, I used DAE to make the visualization of the color, to take the visualization of the colors for the robot joints. But the rest, actually, it's, yeah, maybe not shaded frame, something like that. But if you see it, you know, the others is, you know, we have a mesh of models. You know, the model is a mesh. The model that we have here is a mesh. These meshes are they are making the model. So we have a robot in a mesh format. So you see now the robot is a mesh. You see it is a mesh. So yeah, so this okay, that's so, you know, so you could have a lot of flexibility, but the same can be also done in Gazebo. In Gazebo, actually, we have SRDF file formats, which has also XML file format, which defines the links of the robot and so on. So, for example, something like this, you know, it's something like this. Here you see, it is information about the link. So it tells about the geometry, width, and the height, the position of the origin, the visualizations, and something like that. So if you are really just a person, if you want really to go into the research, or maybe with some projects, you know, maybe having it, now just there are two parallel futures. One is in the research, the second is in the industry. If you are unable to go to industry, using a readily available and standardized softwares like Process Simulate or like SolidWorks, CATIA are the choice, you know. But if you want to work on the research and the development, that means you want to create your own world, yeah. I mean, you know, you want to create your own motion planning and controlling or modeling or something, you know. Just you want to try yourself and to come up with some novel solution, you know, maybe at some point. If you are a person like that, you know, it's better if you consider open sources which are not linked to any commercial softwares. So you are free to implement your own, to disseminate your own works and so on. So if you are really a person like that, I will suggest you to concentrate on ROS, Gazebo, or maybe developing by yourself, like simulation in Unity and something. This is, this is a platform where you develop by yourself. Just Unity is an environment, but it is you who has to create your world. Yeah, that's the second option. So there are two distinct separations in between. So it's up to you to decide and to consider for your future. But the difference is, in Process Simulator, we have a readily available tools which are supporting you for creating the kinematics, for creating the motion, for exporting and exporting the files into computer readable, into the robot readable file formats. But in such ROS or something, it's you who has to create all these things by yourself. If you say move the robot to something, then you have to create by yourself. So that's two very distinction in between these two fields. Yeah, but you are free still to choose both. But yeah, I will try to give you a highlight in both sides. But for our tutorial, of course, we use the readily available solutions. Yeah, so that's all about it. Actually, yeah, since our time is running, I don't want to continue to the next chapter. Actually, now we finished the modeling chapter here, the design requirement and the modeling chapter here. Next week, Monday, we are going to see the mathematical modeling for kinematics, because right now, without the kinematics models, it's nothing. You cannot do anything, okay? Now that you have some know-how how to model the robot with the geometry and with some constraints and so on, but you don't have any clue how to do the kinematics. Without kinematics, the robot doesn't work. So how do we define this kinematics with the mathematical approach? That's what we are going to see next week. Then we see in the other week, we see about the dynamic modeling. Then the next other week, we are going to see the same approach in